Right, looks like it's going. What am I looking for? Uh, shit. Hello. Fuck, my audio's messed up. And that ain't turning on, is it? Alright. Oh, yeah, it's working. I got two separate pieces that are. Something else is patching my audio through, but later. What is doing that? What is doing that? Fucking hell. Oh, that's not good. That'll do the thing I'm telling you. Where is it? Where is it? Right. We got monitor off on both. That shouldn't do shit. Right. I'm just gonna ignore it. Let's just continue. Nobody's gonna be here anyway, I strongly doubt. But hey, this is likely gonna be the last one. At least I'll have this entire thing to myself to prove how long it took me to do this entire thing. Right, so we're going to be turning our single-threaded server into a multi-threaded server. Right now, the server will process each request in turn. Right, where are we on this? Where is the server? We got add, adder, check input, day 1, 2, yep, day 777, hello macro, mini grep, notes, projects, restaurant, Rust gets owned, and source. What? Where is the server? Where is the server? We were making a server just a bit ago. Rust gets owned? What do we got? What do we got? We got guessing game, hello world, add. That's guess owned isn't. Nope, that's not the web server. Right, I'm gonna have to turn off that because I don't want to show other projects. Where is it? What? Where the fuck is this? Really? Come on. We had this going. Add adder checking. Day 1, day 2, 3, 4, 5, 6, 7. Hello? Is it called hello? This shit's called hello. Why is it called hello? Who cares? Sure, it's working now. We got this. Right, that's chill. Okay, now we're ready to go. Right now, yep, it'll process it one by one by one. If the server receives more and more requests, the serial execution would be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished, even if the new request can be processed quickly. We'll need to fix this, but first we'll look at the problem in action. Simulating a slow client on the current server implementation. We'll look at how a slow processing request can affect other requests made to our current server implementation. Listing 2010 implements handling a request for /sleep with a simulated slow response that will cause the server to sleep for 5 seconds before responding. Alright, so inside of main.rs, we are taking in file system, IO prelude, we got a net, thirdly we'll need thread, and time, duration. Alright, under handle connection, we are not changing anything there. We're not changing anything here. Where's status line? Let status line file name match request. Right. So we're taking the if let and we're changing it into a match let. A match request or a match statement. Right. So we're matching request line, the entirety of it. Right. We're just not going to be doing much with any of that. So I'll just move it off. Right. So we're matching on the entirety of request line, and if it is matching the pattern, I guess we could have used this. If it matches the pattern, get HTTP 001. We are going to respond with the tuple. This. We're just going to respond with that tuple. Right, chill. Right, so if the request is at root, we are going to respond with hello.html. Secondarily, we're going to check for the same thing, but it's going to be, that's not what I wanted. It's going to be get/sleep. That's it. This is our router, essentially. And instead, we are going to, creating a new scope. First, we are going to sleep, thread, ::sleep, the duration. From? Oh, okay. I'm guessing from secs just like changes this to milliseconds. I'm guessing if we went just directly to the implementation of this. Nah, duration is an entire thing, I guess. We're creating a new from the enumerable secs. No, a new from, yeah. Taking in secs. The new function, nanos. Oh, so it's in nanosecond? Okay. Well, whatever it's doing, it's doing it. I'm curious what's in duration. Well, yeah, so that's just a second. It is a U64, and then we got nanos, which is of type nanosecond. Always 0 is above nanos per sec. What's nano? Struct nanoseconds is a U32. I wonder why it's a U32 instead of a U64. Ah, who cares? That was Not a good thing to go off on. Hey, who cares though? Alright. And default is going to be this. I would assume. Ah, yeah, default is not what we type. We type an underscore to catch all patterns. Because this is a match statement, we are asking for a pattern. The else is no longer needed. Right, there we go. I'm going to have to assume that'll work. We switch from an if to a match, now that we have 3 cases. We need to explicitly match on a slice of request line to pattern match against the string literal values. Match doesn't do automatically referencing and dereferencing like the equality method does. The first arm is the same as the if block from listing 2019. Sorry, 29. The second arm matches the request/sleep. When the request is received, the server will sleep 5 seconds before rendering the successful HTML page. The third arm is the same as the else block from listing 20-9. You can see how primitive our server is. Real libraries would handle the recognition of multiple requests in a much less verbose way. Would they? Yeah, they would simply break this apart and then get hello from a specific place. Like if we have slash, we would simply get it from whatever our default is, usually like index.html, right? Or whatever is set inside of an environment variable. So yeah, this entire thing would be replaced with something that simply breaks apart everything, taking the request get or any of the other things. But if it is just get, we would assume get and just check against it. Yeah, we would just break this apart, get the pieces that we need, and then direct to the specific place needed. Alright, start the server using cargo run. Alright, let's do that. Ah, very glad. Right. Cargo run. Let's start the server. Where'd the server start at? I've completely forgotten. Ah, yeah. Let's take that, go to it, and let's see. Hello, hi from Rust. Now, if we get to /sleep, it should sleep for 5 seconds. 3, 2, 1, 0. We're getting there. Should it not? It should, but it isn't. /sleep. 1, 2, 3, 4, 5. And then nothing happens. Ah, no, something did happen. Okay, there we go. So she works. Right. Go to /sleep. If you enter the URI a few times, as before, you'll see it respond quickly. But if you enter /sleep and then load /, you'll see that / waits until sleep has slept for its full 5 seconds before loading. There are multiple techniques you could use to avoid requests backing up a slow request. The one we'll implement is a thread pool. Improving throughput with a thread pool. A thread pool is a group of spawn threads that are waiting and ready to handle a task. When the program receives a new task, it assigns one of the threads in the pool But you can't. You you can't hear? You can't hear? I can hear. That's weird. Oh, maybe you can't hear as in like there's something wrong from your end. You can't hear as in like something wrong. See you later. Wait. Um, okay. There could be something wrong with my end. I I'm unsure. It should be fine. Maybe she's on. Hello, is YouTube working? Okay. It seems fine by my end. I'm just gonna continue. Thread pool is a group of threads spawned in a pool waiting for a task, and the program receives a new task. It assigns one of those threads in the pool, and then the thread will process it. The remaining threads in the pool are available to handle any other tasks that come in while the thread is processing. When the first thread is done processing a task, it returns to the pool of idle threads ready to handle a new task. A thread pool allows you to process connections concurrently, increasing the throughput of your server. We'll limit the number of threads in the pool to a small number to protect us from denial of service attacks. If we had our program create a new thread for each request as it came in, so making 10 million requests to our server could create havoc by using up all our server's resources and grinding the process to a halt. Yeah, if you can't handle 10 million requests, you're a little coward. Rather than spawning unlimited threads, then we'll have a fixed number of threads waiting in the pool. Requests that come in are sent to the pool for processing. The pool will maintain a request from this queue, handle the request, and then ask the queue for another request. With this design, we can process up to n requests concurrently, where n is the number of threads. If each thread is responding to a long-running request, subsequent requests can still back up in the queue, but we've increased the number of long-running requests we can handle before reaching that point. This technique is one of many ways to improve the throughput of a web server. Other options you might explore are the fork-join model, the single-threaded async I/O model, or the multi-threaded async I/O model. If you're interested in this topic, you can read more about other solutions and try to implement them. With a low-level language like Rust, all these options are possible. Before we begin implementing a thread pool, let's talk about what using the pool should look like. When you're trying to design code, writing the client interface first can help guide your design. Write an API so the code is write the API of the code so it's structured in the way you want to call it. And then implement the functionality within that structure rather than implementing the functionality and then designing the public API. Similar to how we use test-driven development in the project in Chapter 12, we'll use compiler-driven development here. We'll write the code that calls the functions we want, and we'll look at errors in the compiler to determine what we should change next to get the code to work. Before we do that, however, we'll explore the technique we're not going to use as a starting point. Sure. Just a moment, I'm gonna fix something. Hello, hello, hello. Hello? Alright, that seems to be working okay. The sound's maybe messed up. Hello. Okay. Right. First, let's explore how our code might look if we did create a new thread for every connection. As mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it is a starting point to get working multi-threaded server. Then, we'll add a thread pool as an improvement, and contrasting the two solutions will be easier. Listing 2011 shows the changes we make to main to spawn a new thread for each handle stream within the for loop. Alright, so we do got a 4 for every single incoming listener. We have regular here, it's a stream.onRoute. We don't need that anymore, but we are simply going to thread dot spawn ::spawn, and within that we're going to create a closure, and inside the closure you're going to run the handle connection stream function. Wonder what this is. Oh, well, yeah. Oh, that apparently works. Okay. As you learned in chapter 16, thread spawn will create a new thread and then run the code in the closure in the new thread. If you run this code and load sleep in your browser, then slash in 2 more browser tabs, you'll indeed see that the request to slash don't have to wait for sleep to finish. However, as we mentioned, this will eventually overwhelm the system because you'll be making new threads without any limit. Okay. Creating a finite number of threads. I don't care enough to check this. We want our thread pool, so we'll need a God. What is that? The lock sequence thing. The thing that allows you to run. Yeah, I can't remember what it's called. Where is it? Where is it? Oh, there's just a function for a thread pool. Oh, that's boring. We want our thread pool to work in a similar, familiar way, so switching from thread to a thread pool doesn't require large changes to the code. That uses our API. Listing 2012 shows the hypothetical interface for a thread pool struct we'll want to use instead of thread spawn. Oh, so we actually haven't built the thread pool yet. Okay. So we are building the thread pool. I mean, there's obviously 1,000 different ones, but yeah. Okay. Reference counting is what I was thinking. We use thread pool new to create a new thread pool with a configurable number of threads, in this case 4. Then, in the for loop, pool.execute has a similar interface as thread spawn, in that it takes a closure the pool should run for each stream. We need to implement pool.execute, so it takes the closure and gives it to a thread in the pool to run. This code won't compile yet, so we'll try to compile. But we'll try so the compiler can guide us how to fix it. Oh, so we are just actually typing this in. Fair. Okay, so we're replacing the entirety of that with pool dot. What is it? Execute? Okay. The ring has stopped. And here we are creating a new pool. That pool equal thread pool new. Limiting it to 4. Oops. Right. These things, well, of course that won't work. It says peel. Okay. Thread pool doesn't exist. Use of undeclared type thread pool. Great, our error tells us that we need a thread pool type or module, so we'll build one now. Why did we need to compile that? We know thread pool doesn't exist. This is idiotic. Alright, whatever. So we'll build one now. Our thread pool implementation will be independent of any kind of work our web server is doing. So let's switch the hello crate from a binary crate to library crate to hold our thread pool implementation. After we change to a library crate, we could also use a separate thread pool library to work for any work we want to do using a thread pool, not just for web server requests. Right. Create a what are we doing? Source librs. Source lib.rs. We are creating that. Good stuff. And inside of here, we're simply adding a pub struct thread pool. I think that's about it, right? That's all we're supposed to be doing. Yeah, that's obviously going to do nothing. Right, fine. Use hello thread pool. We don't need that. You're sure. This is going to be outside of this? Sure. That work? Yep, and new is not on it. Well, it still doesn't work, and we can check again. Oh wow, the new function doesn't exist on thread pool. I kind of understand that they're trying to show us compiler-driven, uh, the compiler-driven paradigm, whatever the heck it's called, but like, come on. This indicates that we need to create an associated function named new for thread pool. Ooh, wow. Right. And that's going to be implemented on thread pool. Great. Don't you want us to recompile it again and see if we need to add anything more for it to work? Like a return type? And we are just going to return thread pool. Sure. Associated function this implementation. Dead code. What? Is that an issue? Yeah, it's unused, that's fine. Yeah. New was never used. Dead code on by default. Oh, it's public. We need it to be public because we're yeah. Okay, that's fair. We chose usize as a number of size parameter because we know that a negative number of threads doesn't make any sense, so it needs to be unsigned. We also know that we'll use this this 4 as a number of what? We also know we'll use this 4 as the number of elements in a collection of threads. Sure, which is what the useSize type is for, as discussed in integer types section of chapter 3. Okay, sure. No method named execute for struct. Cool. Yep, we need to create execute. Execute. Does that need to return anything? Pub. Evan. Oops. Nope. We're implementing it on thread pool. Public function execute. We don't need two of these. Why do I have two of these? Doesn't this need to... What does this take in? This probably takes in what? It takes in a... Oh god, how do we... Yeah, right now the occurs because we don't have a execute method on thread pool. Recall from creating a finite number of thread section that we decided our thread pool should have an interface similar to the thread spawn. In addition, we'll implement execute function so it takes closure it's given and gives it to an idle thread in the pool to run. We'll define the execute method on thread pool to take a closure as a parameter. Recall from moving captured values out of the closure and the FN trait section of chapter 13 that once we take closures as parameters in three different traits, that we can take closures as parameters with three different traits, FN, FNMute, and FN1s. We need to decide which of the closures to use here. I can't remember, I'll admit. Probably... Each of these is only going to be run once, but... No, but actually. We know we'll end up doing something similar to the standard library thread spawn implementation, so we can look at what bounds the signature of thread spawn has on its parameters. The documentation shows us the following. Does it? I'm curious. If this is what they're going to ask us to be doing, then what does the documentation actually show? Oh, exactly what it said. Okay. Yeah, that's useful. Kind of thought they'd lie to us. Hey. Right. The F-type parameter is the one we're concerned with here. The T-type parameter is related to the return value, and we're not concerned about that. We can see that spawn uses FN once as the bound trait on F. This is probably what we want as well, because we'll eventually pass the argument we get in execute to spawn. This has been closed the entire time. And it's incredibly dark in here, so you can't see shit anyway. That's going to be more distracting than helpful in it. You don't need to see my gorgeous little thing. Right. I'm just going to skip up to here, honestly. The F-type parameter... Oh, no, maybe not. We can further... Alright, where is it? Where did we end? This is probably what we want, because we'll eventually pass the argument we get in execute to spawn. We can be further confident that with FN once, the trait we want to use is the trait that we want to use, because the thread for running a request will only execute that request closure one time, which matches the once in FN once. The F-type parameter also has the trait bound send, and lifetime bound of a static, which are useful for our situation. We need send to transfer the closure from one thread to another, and static because we don't know how long the thread will take to execute. Let's create an execute method on the thread pool that will take a generic parameter of type F with these bounds. Right. So we are going... Why create two impl blocks? You impl... self. Imbecile is what I want to say. But I'm an idiot. Right, so we're going to take in a reference, self, F, of type F, which is being brought in here, or specified here. That is a generic. Where F is FN, FN once. Also implementing send. With a static lifetime. That is incorrect. And here is the rest of it. Well, we could make it match more the no, I don't care that much. Huh. Okay. We still use the brackets after f(1) because this f(1) represents a closure that takes no parameters and returns the unit type of an empty tuple. Just like function definitions, the return type can be omitted from the signature, but even if we have no parameters, we still need the parentheses. Reasonable? Again, this is the simplest implementation of the execute method. It does nothing, but we're trying to only make our code compile. Let's check again. Oh, well, that would help. Thread execute. That's not what it was complaining about. It was complaining about. Cool. Yeah, and it's got a warning right here. Hey, you got any errors? No, we don't. Seems like she's working, but we got some warnings. Because we're not using things. It compiles! But note that if you try and do CR and make a request in the browser, you'll see some errors in the browser. We saw in the beginning of the chapter. Site can't be reached. Because we're not doing anything in execute. We haven't even passed it in. Sorry, we have passed it in. We're just not doing anything. Note, a saying you might hear about language is with strict compilers such as Haskell and Rust is, if the code compiles, it works. But this saying is not universally true. Our project compiles, and it does absolutely nothing. And it works perfectly at doing absolutely nothing. If we were building a real complete project, this would be a good time to start writing unit tests to check that the code compiles and has the behavior we want. Yeah, we're not doing that though. We aren't doing anything with the parameters to new and execute. Let's implement the bodies of these functions with the behavior we want. To start, let's think about new. Earlier, we chose an unsigned type for the size parameter because a pool with a negative number of threads makes no sense. However, a pool with 0 threads also makes no sense, yet 0 is a perfectly valid usize. We'll add code to check that the usize is greater than 0 before returning a thread pool instance, and have the thread panics if it receives a 0 by using the assert macro, as shown in listing 2013. What? So within execute? No, within new. Oh, okay. Yeah, that's where we're doing things. Apology. Assert. Size is over or equal to, no, not equal to 0. Good stuff. We have some, sure. We are going to create a new thread pool. The size is the number of threads in the pool. Hashtag panic. The new, oops, function will panic if the size is 0. Period. Wow, I'm really not good at spelling today, am I? Why is this here? Out of curiosity, does Rust have anything which would check that? No. No, of course not. Maybe it does, but Hey, who cares? We've also added some documentation in our thread pool with doc comments. Have we? It doesn't work with the LSB. The LSB does not like it. Note that we follow good documentation practices by adding a section that calls out the situation in which our function will panic, as discussed in Chapter 14. Try running cargo doc open. Cargo doc open. Dash open. Yep, that'll bring up thread pool. Yeah, I can see that in this browser, but I'm not going to show it over here. Who cares? No. Let's show it. Because I want to explore it a bit. Yep, so we got the public function new and execute. We got fn once, but we don't actually have any documentation on new. The doc block has not done anything. We see what the generated docs for new looks like. No, we don't. No, we don't. We simply don't see that. That's not true. Oh, it is in the wrong location. My God, I'm an idiot. That is where it should be. Okay, thank you. Thank you. And if we refresh... Nope. Thread pools. New. Still hasn't come up. Nope. Sure. I don't care. We've also added some... Yep. Instead of adding the assert macro as we've done here, we could change new into build and return a result like we did with config build in the IO project in listing 12.9. But we've decided that in this case that we're trying to create a thread pool without any threads, and that should be an unrecoverable error. If you're feeling ambitious, try to write a function named build with the following signature to compare with a new function. I'll do that on my own later. Maybe. Creating space to store the threads. Now that we have a way to know we have a valid number of threads to store in the pool, we can create those threads and store them in the thread pool struct before returning this struct. But how do we store a thread? Let's take another look at the thread spawn signature. Right. It outputs a join handle. I don't know what that means, to be honest. The spawn function returns a join handle, where T is the type of a closure that the closure returns. Let's try using join handle 2 to see what happens. Okay. So inside of execute, we are going to be outputting a join handle. Yep, with T as the type. Meaning we're also going to need to have T being brought in here. Well, that's wrong. Yeah, because we're not returning shit. The spawn function returns, yep. So let's try using join handle 2 to see what happens. In our case, the closure we're passing to the thread pool will handle the connection and not return anything, so T will be the unit type, nothing. I don't know how to do that. What are we doing? It's just going to be outputting... I don't care. The code in listing 2014 will compile, but doesn't create... Sure, any threads yet. We've changed the definition of thread pool to hold a vector of thread join handle instances, initialized with vector... Initialize the vector with a capacity of size set for a for loop and returned a thread pool instance containing one. Right. So in our live.rs, use standard thread. Yeah, we don't need join handle. Right. So the public struct thread pool is going to contain threads with a vec holding a thread. Thank you. Thread join handle. Okay, sure. That's what I'm looking for. I'm an idiot. I'm kind of an idiot. Why would we put that in execute? Why would execute return anything? Execute won't return anything. I am a fool. Nope. Oh. What's wrong? Public struct thread pool. Yep, with threads. Type vec. Thread join handle. Yep, I see. Yeah, we need to use thread. Yep. You can just get that yourself. Thread pool is defined here. Congrats. And of course, this won't work because we're doing nothing inside new yet. And we are creating new stuff with new, right? So we are asserting, we won't need this anymore. Let a mutable threads equal a vec with capacity of whatever the size is. And then for, we're not using an iterator, in 0 to size. Create. All right, so we're not. Are we doing that ourselves? Sure, whatever. I'm just gonna continue on some threads and store them in a vector. I'm not going to do that yet. Because I'm going to assume expected thread pool. Yep. Creating a new thread pool. Holding threads. Are we doing this later or not? We don't know. It's just saying this here. If we don't get to it, I'll just do it myself. We brought in standard thread into scope in the library crate because we're using thread join handle as the type of the items in the vector thread pool. Once a valid size is received, our thread pool creates a new vector that can hold size items. With the with capacity function, make sure that it only has that size because we know we need to store the size element of the vector. Doing this allocation up front is slightly more efficient than using vec_new, which resizes itself as elements are inserted. When you're on cargo check again, it should be successful. Is it? Not sure. Cargo check. Yep, some warnings because we haven't done anything. A worker struct responsible for sending code from the thread pool to a thread. You left a comment in the for loop in listing 2014. Just put it as a to-do. It would make it much easier because maybe you're asking me to do this. We can. We have the knowledge. I'm getting angry for no reason. Apologies. Here, we'll look at how we actually create threads. The standard library provides thread spawn as a way to create threads. And thread spawn expects to get some code the thread should run as soon as the thread is created. However, in our case, we want to create the thread and have them wait for code that will send later. The standard library's implementation of threads doesn't include any way to do that. We have to implement it manually. We'll implement this behavior by introducing a new data structure between the thread pool and the threads that will manage this new behavior. We'll call this structure worker, which is a common term in pooling implementations. The worker picks up code that needs to be run and runs the code in the worker's thread. Think of people working in the kitchen in a restaurant. Yep. Instead of storing a vector of join handle instances in the thread pool, we'll store instances of the worker struct. Each worker will store a single join handle instance. Then we'll implement a method on worker that will take a closure of code to run and send it to the already running thread for execution. We'll also give each worker an ID so we can distinguish between the different workers in the pool when logging or debugging. Here is the new process that will happen when we create a thread pool. We'll implement the code that sends the closure to the thread after we have worker set up in this way. Define a worker struct that holds an ID and a join handle. Define thread pool to hold a vector of worker instances. Define a worker new function that takes an ID number and returns a worker instance that holds the ID of a thread spawned with an empty closure. In thread pool new, use the for loop counter to generate an ID, create a new worker with that ID, and store the worker in a vector. If you're up for the challenge, try implementing these changes on your own before looking at the code in listing 2015. Yeah, I don't care. I'm just going to continue on with this. Right. So we are first going to change threads, which we never used, into workers, which is going to be a vector of workers. We don't have a worker, because it's going to be done later, of course. Why is it down there? Does this need to be public? No, it doesn't. Which is going to hold the thread. I'm assuming it's the thread. Yep, and the ID. Wow. Holding in nothing. And of course the ID, which is going to be, I would assume, a U size. Yeah, it's U size. Good stuff. So implementing on thread pool. Here we're going to implement on worker. What are we doing? We got let workers. Why did we type any of this? For ID. Yep. Sure. Workers probably, I'm not looking at that. Workers.push. What is it? Push. The value will likely be something along the lines of well, it's a vector, right? It's a vector, so it'll have to be a worker dot new, which we haven't implemented, which will probably take in a tuple with the ID. Why would it take in a tuple? ID and the no, we don't have anything that we want yet. So we're just creating a list of this. Sure. Now let's check. What does it say? We got a ID and to size. Yep. Yep. New ID. Yeah, we're just keeping that. Workers. Right. Meaning we'll need to implement on worker. Don't need that. On worker, we'll need to implement the function new. Which will return a worker. Is that how you do? I can never remember. Is that how you do? Yeah, it is. Good. Function new worker will take, we'll just, sure. Worker where ID, yeah, we'll just create a random thread here. So the ID will be what's brought in here. ID. ID is ID. And the thread will, I actually can't remember how to do join handle. It's probably like something like a join handle. I actually don't know, so let's just check. That's note. Oh, yeah. Yeah, because sorry. Yep. Now that is a failure on myself, I will fully admit. I wasn't paying too much attention. Yeah, because thread spawn creates a join handle with an empty closure. Yep, sure. What do you mean unexpected token? Is that chill? Oh, yeah. There we go. Chill. That'll work. Is that it? That's probably it. No, it's not. Oh, yeah, yeah. This has got to be a capital. Oh, not dot. There we go. It's still an error. Can't find worker. Of course you can't. No references found to this position. Sure. There's still some errors. Oh yeah, we're putting in the ID. Still some errors. View size. Yep. Got that. Still some errors. Yep. Any errors? Yep, 2. Missing a type for the function parameter is going to be a usize. Anything else? Nope, just warnings. Alright. And we're still not doing anything in the execute. We've changed the name of the fields in the thread pool from threads to workers because it's now holding workers instead of instances of join handle instances. Yep. We use the counter for the for loop as an argument to the worker new, and we create a new worker for each. Yep, and we add that to the vector. External code, like our servers, main.rest, doesn't need to know the implementation details regarding a worker within the thread pool, so we make the worker struct and its new function private. Yep. The worker new function uses the ID we give it to storage. Yep. Instance that is created by spawning a new thread using an empty closure. If the operating system can't create a thread because there aren't enough system resources, this will panic. That will cause our whole server to panic, even though the creation of some threads might succeed. For simplicity's sake, we don't care. But we should instead use thread builder and its spawn method that returns result instead. Okay. This code will compile and will store the number of worker instances we specified as an argument to thread new, thread pool new, but we're still not processing the closure yep, still not doing anything with it. The next problem we'll tackle is the closure given to thread spawn do absolutely nothing. Currently, we get the closure we want to execute in the execute method. But we need to give the threads, currently we get the closure we want to execute in the execute method, but we need to give thread spawn a closure run when we create each worker during the creation of the thread pool. We want each worker struct that we just created to fetch the code to run from a queue held in the thread pool and send that code to the worker's thread to run. Yep. The channels we learned about in Chapter 16, a simple way to communicate between two threads, would be perfect for this use case. I don't remember very much about that, to be honest. It's going to ask me to do it myself? No. I'll admit I wouldn't be able to do that. We'll use the channel function as the queue of jobs, and execute will send a job from the thread pool to the worker instances, and yep, here's our plan. The thread pool will create a channel and hold on to the sender. Each worker will hold on to the receiver. We'll create a new job struct that holds the closure we want to send down the channel. The execute method will send the job it wants to execute through to the sender. In its thread, the worker will loop over its receiver and execute the closures of any jobs it receives. Let's start by creating a channel in thread pool new and holding the sender in the thread pool instance as shown in lesson 2016. The job struct doesn't hold anything new for now, but will be the type of items we're sending down the channel. Okay. So we are also going to use, thank you. So we're using standard thread and sync MPSC. What's wrong? That's exactly what that is. Use stand. Oh my god, I'm an idiot. Sure. Yep. Alright, so we're doing the same. Now we're holding the workers, and now we're holding a list of sender, which is a multi-process. Oh god, what is it? Multi-producer, single consumer. Sender of type job. We don't have a job structure right now. Nope. Idiot. Job doesn't exist. Sure. Let's create the struct. Job. All right. Inside of the thread pool. Inside of new. That mutable. Right. So before all of this, we are going to be creating a new sender and receiver. Shoot. Which is a tuple. Because a tuple is returned. Equal MPSC. Multiple producer, single consumer. Channel. Let mutable worker, vector size, good. The ID is fine. And at the end of this, we are simply also adding our sender into the new thread pool. Oh my lord, I am bad at this. Right, chill. We're not doing anything with receiver currently because we're not doing anything at all. We're just slowly adding in things with no context. In thread pool new, we create our new channel and have the pool hold the sender. They will successfully compile. This will successfully compile. Let's try passing receiver of the channel into each worker. Okay. Now we're taking this in. Sure. Receiver. What is this? Of type? Of type what? With holding a... Sure. Unused. Good. Right? We know we want to use the receiver and the thread. Right, let's try passing the channel into each worker as the thread pool creates the worker. We know we want to use the receiver in the thread that the workers spawn, so we'll reference the receiver parameter in the closure. Right, so we're passing in receiver. I can't remember how to do that, to be honest, what I'm doing there. That's definitely not what we want to do. I can't remember what we want to do. Yep, that's correct. And inside here, we are simply going to... Yeah, that was definitely not what we wanted to do. And we're just passing that out. Is there anything else we're doing here? Nope. Looks like I got that about right. I'm an idiot, though. We didn't want to create a new parameter. We didn't want a closure with the parameter, which is the receiver. We simply wanted to capture receiver within the closure from the greater context, which is the parameter being brought in with the new function of the implement worker. So on our actual API, they won't even have to know that it uses a receiver. We aren't actually changing this in any fashion, so main shouldn't have to make any difference, any changes to make this work right. We've made some small and straightforward changes. We pass the receiver into worker new, and then we use it inside the closure. When we try and check this code, we get this error. What is this? Right. Inside this loop, receiver value moved here. What? What is the error? Use of moved value receiver. Right, so we created this. Move occurs because receiver as type that does not implement the copy trait. Value is moved here. Previous iteration of the loop. Yep. The value is moved. Consider changing this parameter in the type method new to borrow instead of owning the value. If owning the value isn't necessary, do we need to own the value? I think we do. This parameter takes ownership of the value. Help consider moving the expression out of the loop so it is only moved once. That's the issue. Yeah, because this is a loop. We're trying to move it multiple times, creating a new thread. Yeah, that's an issue. So we're gonna have to are we gonna have to use an RC or something like that? I don't see how that works, to be clear. I can't remember, to be honest. The code is trying to pass receiver to multiple working instances. This won't work, as required from chapter 16. The channel implementation that Rust provides is multiple producer, single consumer. Yeah, this means we can't just clone the consuming end of the channel to fix this code. We also don't want to send a message multiple times to multiple consumers. We want one list of messages with multiple workers such that each message gets processed once. I don't know how to fix that. Additionally, taking a job off the channel queue involves mutating the receiver. So the thread needs to be a safe way to share once, otherwise we might get a race condition as in chapter 16. Recall the thread safe smart point just discussed in chapter 16. To share ownership across multiple threads and allow the thread to mutate the value, we need to use an arc mutex. The archetype will let multiple workers own the receiver, and mutex will ensure that only one worker gets a job from the receiver at a time. Yep, because we're locking it. Listing 2018 shows the changes we need to make. Right, so we are going to be bringing in, within sync, sure. We are also going to be bringing in arc and mutex. Unused. I can't remember how to use those. Alright. We are going to need in here. Yeah. You're going to shadow receiver. I've misspelled receiver. But I've misspelled it consistently, so it's fine. A new arc holding in a mutex, which is also new, with a receiver. With the receiver. And then receiver is going to be cloned. And we're going to have a reference to this because you don't need ownership over a receiver here. And that's kind of the entire point. Oops. Also, we need to change worker. It's probably down there. I can't see it though. Instead of taking a receiver, we want to take in a receiver, which is a type of arc, holding in a mutex, holding in a multiple producer, single consumer receiver, holding in a jump. Is that correct? What? What's wrong here? Yeah, that's spelled incorrectly. Reviver. Oh, there we go. Is that correct? Yeah, there we go. Right? A receiver will be an arc, mutex, multiple producer, single consumer, receiver holding a jump. Okay. Oh, this is terrible. That is disgusting. Opening worker. Yep. In Threadpool New, we put the receiver in an arc and a mutex. For each new worker, we clone the arc to bump the reference count so the workers can share ownership of the receiver. With these changes, the code compiles. We're getting there. Implementing the execute method. Let's finally implement the execute method on Threadpool. We'll also change job from a struct to a type alias for a trait object that holds the type of the closure that execute receives. As discussed in the Create Type Synonyms with Type Aliases section in Chapter 19, type aliases allow us to make long types shorter for ease of use. Look at listing 2019. Oh, thank God! Look at this. We can just delete this. Oh, no, we can't. We're doing it for job. Sure. I mean, we could, but we won't. Sure, so job is not going to be a struct. It is going to be a box, which is a dynamic. Dynamic fn once with send and static. What's wrong with this? Nothing. What? Yeah, because this isn't a... Yeah, you can. What are you talking about? Oh. Yep. Sure. Right? What's wrong here? Use drop to clarify the intent. That's a help. And it's probably okay. Where's execute? Right, we're not actually returning anything, of course. We are going to let job equal a box holding F. Okay. Self dot sender dot send job dot unwrap. Right, what's going on here? We have sent job, which is holding the closure and unwrapping it. I'll admit I don't really know what's going on here. Creating a job type alias or box that holds each closure and then sending the job down the channel. Right, yeah, so job will be a new box which is sent down the channel. And inside the box is holding a function which is a closure of the type specified, which is a... Is that just job? I don't know. No, yeah, that's... This is the type that it'll be anyway, but you know. After creating a new job instance using closure we get in execute, we send that job down the sending end of the channel. We're calling unwrap on send for the case that sending fails. This might happen if, for example, we stop all our threads from executing, meaning the receiving end has to stop receiving new messages. At this moment, we can't stop our threads from executing. Our threads continue executing as long as the pool exists. The reason we use unwrap is that we know the failure case won't happen. But the compiler doesn't. We're not quite done yet. In the worker, a closure being passed to thread spawn will still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiving end of the channel for a job and running the job when it gets one. Let's make the change shown in listing 2020 to worker new. Worker new. Right, so this is just going to be a loop. So within each thread, we have a loop that creates a job equal a receiver, or receiver.lock. We are locking the receiver to make sure nobody else can touch it. We are unwrapping it. Rec v, can't remember, unwrap. What's the problem? Receiver is not real. Yep, reviver again. That's cool. Why is there a 0? After this, we're going to print saying a worker with the ID got a job. Executing. Then we're just going to take the job and run it. What's wrong? What's wrong here? There's some warnings. Here we first call lock on the receiver to acquire the mutex, and then we call an unwrap to panic on any errors. Acquiring a lock might fail if the mutex is in a poison state, which can happen if some other thread panicked while holding the lock rather than releasing the lock. In this situation, calling unwrap to have this thread panic is the correct action to take. Feel free to change this unwrap to an expect with an error message that is meaningful to you. If we get the lock on the mutex, we can call recv to receive a job from the channel. A final unwrap moves past the errors as well, which might occur if, the call to recv blocks, so if there's no job yet, the current thread will wait until a job becomes available. The mutex ensures that only one worker thread at a time is trying to request a job. Our thread pool is now in a working state. Try it. Nope. I forgot to put move on, didn't I? Hello? Oh. Yeah, that's why we have all of these errors. Right, so we got workers. Yield is never read. ID is never read. Thread, yep. Success. We now have a thread pool that executes connections asynchronously. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot of requests. If we make a request to sleep, the server will be able to serve other requests by having another thread run on them. Note, if you open sleep in multiple browser windows simultaneously, they might load one at a time in 5-second intervals. Some web browsers execute multiple instances of the same request sequentially for caching reasons. This limitation is not caused by our web server. After learning about the while let loop in chapter 18, you might be wondering why we didn't write the worker thread code as shown in this listing. Right, well let okay, as long as it's good, receive.lock and wrap recv enter job. Right, yep. Why not use a well let instead of our loop? The code compiles and runs, but doesn't result in the desired threading behavior. A slow request will still cause other requests to wait to be processed. The reason is somewhat subtle. The mutex struct has no public unlock method, because the ownership of the lock is based on the lifetime of the mutex guard within the lock result mutex guard of any type that the lock method returns. At compile time, the borrow checker can then enforce the rule that a resource guarded by mutex cannot be accessed unless we hold the lock. However, this implementation can also result in the lock being held longer than intended if we aren't mindful of the lifetime of the mutex guard. The code listing 2020 that uses let job equal receiver lock unwrap recv unwrap works because with let, any temporary value used in the expression on the right-hand side of the equal sign are immediately dropped when the let statement ends. However, with a while let, and if let and match, does not drop temporary values until the end of the associated block. In listing 2021, the lock remains held for the duration of the call to job, meaning our other workers cannot receive jobs. Alright, last little bit of this. Graceful shutdown and cleanup. The code listing 2020 is responsible. Right, honestly, I'm incredibly tired. I've not been doing great. I think that's about it for today. Wish y'all the best. Peace out. This is goodbye.